We are the Tenacious Tigers, and we have designed a Pillbug-inspired robot. Now, robots can be really useful in a lot of different situations that are dangerous or difficult for humans to navigate. This includes environmental monitoring, where humans may not want to be out in the wilderness for so long or may encounter dangerous wildlife. Space exploration, where humans require suits and other things to help preserve their life in environments that are hostile. Or in search and rescue, where there is a lot of instability, rubble, small spaces, other things that really make it difficult for humans to do tasks. Now, robots can be more robust, they can be smaller, move in different ways that give them an advantage in these situations. When designing robots for these situations, there are a few different methods, one of which is bioinspiration, where different materials, movements, or animals in nature are looked to help guide the design of the robot. In this case, we decided to design a robot based off of the pillbug. The pillbug, otherwise known as the roly-poly, is a very common creature that can be found in a wide range of environments. These terrestrial isopods get their nickname pillbug or roly-poly from the fact that when threatened, they will roll up into a defensive, balled-up posture and then will later relax when they feel safe again. So, based on these behaviors, we made a robot with two main goals. The first, that it would be able to roll down via gravity by forming a spherical shape in a curled up posture. And the second, that it would be able to withstand more crushing forces with this protective outer shell than it would be able to without it.
Our analogy table is essentially the same as our project proposal. The pillbug's behaviors of rolling up and walking as locomotion remain the same on our robot. And we've proved that we can make the robot roll downhill with gravity. It still says unsure because it's not fully similar and that our downhill movement is purposeful. Additionally, we have a different number of legs. We have the same as the original Robogami form, which is 6 legs, and the outer shell or cuticle is the same in that it covers the electronic components, or in the case of a pillbug, the guts. It's not the same material, but we are fairly sure that the materials act in the same in terms of mechanical properties. The size is different, as the pillbug, its machine itself, is quite large compared to the teeny tiny little pillbug. Functional mechanisms, it still has the spherical shape to roll downhill with gravity. As for characteristics, it does withstand crushing force, and performance criteria, it is protected from forces with conglobation.
For a pillbug-inspired robot, we went through multiple shell iterations before coming to our final design. Our first idea was to use paper, but we realized quickly that this was hard to iterate off of, and it led to slow prototyping, but most importantly, it did not bend to form a sphere. Next, we tried a CAD design, but this CAD design also did not form a sphere because the pegs would break easily. Finally, we found a design on Thingiverse. However, we found an issue, which is that the pillbug forms a sphere with 10 pieces, but these 10 pieces, when in the unrolled up state, do not lie flat. So we deduced that we needed to design a head and tail piece to form a ball and have the unrolled pillbug lie flat. After designing the head and tail piece, we figured out that it still does not lie flat, and it also falls onto its side when in the rolled up configuration because it resembles more of a disc than a sphere. So to address these last issues, we widened the shell in 3D Printer OS by 40% in the Y direction, and we found that when printing a very tiny prototype, the shell lied flat and it did not fall over when in the rolled up configuration because it was more spherical. So in our final design, we printed the shell at full size to fit around the Robogami body without bending, and we also thinned the shell to reduce print time. However, we had an unforeseen issue, which was that the shell itself was too big and heavy for the Robogami to support. So our final size adjustment was to decrease the shell size by a small amount and to put cuts into the robogami body so that it would bend as the shell rolled up around it.
After designing the shell, the next component to be designed was a rolling actuator. The rolling actuator is supposed to move the shell pieces to form a sphere. For this actuator, we had different possibilities. In the end, the cable pull system was used as it was the easiest way to close the shell with the least amount of components, which made the setup light and simple. We then had to decide whether to use continuous servo motors or DC motors to actuate the cable pull. In the end, we decided to use continuous servo motors, as these are easy to implement with our other servo motor, which is actuating the walking mechanism. It also used the same electrical setup and was known by the team. To guide the fishing line, we used O-rings at the side of the shells, and a spool was attached to the servo motor to pick up the fishing line. The servo motors in the robot are controlled by an Arduino Uno, which the team is communicating to via Bluetooth. Here you can see the code that was used. On the left, we have the different cases to communicate to with the Bluetooth. The first two are for the walking of the robot, and the third and fourth case are for the curling up and uncurling of the robot. These cases then activate different states of the Arduino, which then actually tells the Arduino how to move the individual servo motors. Here we can see the different iterations and testing states of the rolling up actuator. In the beginning, we started to just attach fishing line to the shell pieces and pulled them by hand to see whether this would close the shells. After that, we attached the servo motor to the shell and tested whether that would close up the shell. We also needed this step to adjust the speed and duration of the pulling to see whether this would close the shell and to make sure it would not rip off any of the guiding O-rings. The final step was then to integrate the robot base and see whether the shell would still be able to close and whether the servo motor had enough strength to close the shell around the robot body. The last step was actually turning around the shell and seeing if it could still curl up with facing down.
Once the shell was designed and the actuation was designed, this all had to be combined into one robot. We decided to attach Velcro-tipped springs to the inner base body robot that were tall enough to allow some compression while still protecting the Arduino and other electronic components on the robot. We then attached these to the shell via the other end of the Velcro in order to make a non-permanent connection that would allow the body and the shell to be separated in order to access any of the electronic components.
For our methods of testing, we looked at two important factors, crushing and rolling downhill. Static load was applied with weights. Our objective was to see if the robot would hold up the weight both with the shell and without, and compare. Our observations were noted, and we tested in increments from 0.02 pounds up to 15 pounds. For rolling downhill, we placed the robot on an incline, and our objective was to see if the robot would roll by itself without being pushed or not. We noted observations, and we adjusted the angle of inclination from 0 degrees to 20 degrees with a change of 5 degrees.
The crush testing actually showed out what we expected, that the shelled robot can withstand more load than the base robot. It was able to withstand up to 15 pounds of static load, which is double the weight than the base robot was able to support. After the maximum load, the rebound was reduced but not gone, and the robot came back to the original shape.
We noticed that the robot at 5 degrees did not always roll on its own, but at 10 degrees and higher it did, and at higher grades it would roll quicker and also straighter at 20 degrees with almost a perfectly straight roll down that hill. We also attempted placing the robot perpendicular to the angle it would normally be facing if it had been facing forwards intending to go downhill, just to confirm that it would roll as expected in different orientations, as that is one of the benefits of having that spherical shape. We did see that the robot rolled exactly the same on its side as it did when facing directly downhill, which did support our hypothesis of the spherical shape being beneficial.
To conclude, we were able to successfully design and fabricate a pillbug-inspired robot. Our robot successfully conglomerates, has an improved loading capacity, and rolls down an incline. In future improvements, we think it would be beneficial to focus on the rolling up and unrolling mechanism. While it almost fully rolls up, it doesn't unroll at all currently. We think an additional mechanism needs to be added to make it unroll successfully. Furthermore, to be applicable in real-world situations, we think it would be beneficial to make the robot more autonomous by improving upon its ability to walk and giving it the ability to sense an incline. Lastly, this robot is very large compared to an actual pill bug, and we believe that its large size limits it in its actual applicability currently. Thank you for taking the time to listen to us. We are the Tenacious Tigers.